Welcome to today's webinar on the topic of design of structural stainless steel. The webinar is organized by the New Zealand Stainless Steel Development Association, the University of Canterbury in Christchurch, supported by the Steel Construction Institute, and conducted by the International Molybdenum Association and the Nickel Institute. Today's presenters are Ms. Nancy Bedoux, Associate Director at the Steel Construction Institute and consultant to the Nickel Institute, as well as Dr. Francisco Meza, Principal Engineer at the Steel Construction Institute. Our panelists of today are Dr. Kyu Tsiang, Lecturer in Structural Engineering at the University of Canterbury in Christchurch, and Paul Geppert, Executive Director of the New Zealand Stainless Steel Development Association. I'm your host today, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar.
Hello, everyone. I would like to welcome to everyone to this second webinar, where we are going to tell you about the differences between the structural performance and design of stainless steel and carbon steel structures. So first, I'm going to tell you about the differences between the performance of stainless steel and carbon steel structures. And then I'm going to hand over to Nancy Bedoux, who will tell you about the different stainless steel standards that are available. And also, she will point out some of the differences between the design rules that are given for stainless steel and carbon steel structures. At the end of the webinar, she will also tell you a little bit about the design of stainless steel connections. Okay, so we will start by looking at the stress-strain characteristic of stainless steel and carbon steel. This figure shows typical stress-strain curves for the main three stainless steel alloy families, and also a typical stress-strain curve for a mild carbon steel grade. Duplex stainless steels are the strongest out of the three alloy families, and austenitic stainless steels are the one that show the most significant nonlinearity. And by nonlinearity, I mean that the stress-strain behavior deviates from the linear behavior that is characteristic for carbon steel before the yield strength is reached. Now, for carbon steel, the yield strength is well defined, and it corresponds to the point at which further increases in strain result in no increase in stress. And the region in which the stress does not increase with the strain is referred as to the yield plateau. For stainless steel, the yield point is not well defined, and as you can see in this figure, the stress-strain curve shows this rounded shape without a sharp yield point. So because of this, the yield stress of stainless steel is obtained by offsetting the initial modulus of elasticity, which is represented by this inclined red line. And this line is offset to a strain of 0.2%. Then the point at which the red line intersects with the stress-strain curve is considered to be the yield stress. Now, you can probably not see it very clearly in this figure, but once you reach the yield strength of the stainless steel, if you continue straining the material, the stress will continue to increase gradually. So there is no plateau, as is the case in the mild carbon steel. So this increase in strength beyond the yield stress is what we call the strain hardening. And some of the design rules that are developed for stainless steel structures try to take advantage of this strain hardening. So here I'm showing you the full stress-strain curve for the three different stainless steel alloy families, as well as for the carbon steel grade. In the figure, you can see in this figure you can see more clearly the strength hardening of stainless steel. You can also see that carbon steel shows some strength hardening after the yield strength is reached. But in order to develop this strength hardening, the strain in the material has to exceed the yield plateau. Now, from this figure, there are also other properties of stainless steel that you can compare against the one for carbon steel. And one of them is the ductility, which can be represented by the elongation at fracture. So you can see that the elongation at fracture of austenitic stainless steel is significantly larger than the one for mild carbon steel. And the one for duplex and ferritics is similar. Now, the large amount of ductility that stainless steel offers is beneficial for applications in which you need the material to be able to redistribute stresses. And it is also needed for seismic applications in which you need the material to be able to sustain large plastic strains so that you don't have premature failure due to fracture. So the shape of the stress strain curve of stainless steel has an effect on three aspects of design, which I'm going to discuss in a bit more detail. The first one is the strength due to strength hardening. This slide shows some of the benefit associated with strength hardening. A clear example of this benefit is that it provides a margin of safety in those situations in which the resistance of the member is governed by yielding. So for example, if we imagine that we have a tensile member that is proportional to resist a tensile force by yielding of the cross-section, when the force, the stress in the cross-section, when this force is applied, the strain in the cross-section is going to be equal to the yield stress if we assume that the section is fully utilized. Now, if for any reason the force that is applied to the member is slightly larger than initially anticipated, due to strength hardening, the member will still be able to resist increases in load by developing stresses that go beyond the yield stress. Now, you have to be aware that in order to take advantage of this strength hardening, the material will have to strain significantly more than if it was working at stresses that are below the yield stress. But if the formations are not an issue for you, you might want to take advantage of this additional strength. And in fact, there are some design provisions that have been developed specifically for stainless steel, which will try to take advantage of this additional strength. Another example in which strength hardening is beneficial is when you have a beam that is designed to develop its plastic bending moment capacity. So in this case, the beam is assumed to yield through the entire cross-section. But now, in reality, the portion of the beam cross-section that is closer to the neutral axis does not really yield. And the reason we can assume that the entire cross-section yields is because the fibers of the cross-section that are further away from the neutral axis are able to develop strength hardening. And this strength hardening compensates basically for the lack of yielding in the portions that are closer to the neutral axis. Now, bear in mind that due to the gradual loss of stiffness of stainless steel, the portion of the cross-section that doesn't reach the yield strength is larger than for a carbon steel beam. So in this case, strength hardening is very beneficial for stainless steel. The large strength hardening of stainless steel also result in an increase in strength that result from cold work. So this increase in strength is particularly large for austenitic stainless steels, which are the ones that show the largest amount of strength hardening. So the type of sections that can benefit from an increase in strength due to cold work are cold roll hollow sections or cold form sections like channels, for example. This graph you can see here shows why the strength of stainless steel increases as a result of cold forming. So when these sections are fabricated, you start from a sheet which might be in the anneal condition or might already have some amount of cold work that is applied in order to achieve the desired thickness of the sheet. So in this graph, you can see the stress strain curve of the stainless steel sheet. And as the stainless steel sheet is bent to form the structural shape, the stainless steel material is deformed plastically, following the loading and unloading path that the red curve in the figure is showing. So the stress strain characteristic of the cold form section will then be given by the blue curve that is showing in the figure. Now, the amount the strength in the steel increases depend on the amount of plastic deformation. And because of this, different part of the cold form section will have different level of strength enhancement, depending on how much they have been deformed. For example, the corners in the square hollow section will have a larger strength than the flat part. And you will see that the design codes for stainless steel give provisions to account for this increased strength when designing this type of members. Now, one important thing to take into account is that you cannot consider the effect of strength enhancement when designing a cross-section that contain a weld or that is adjacent to a weld. And this is because of the annealing effect of the weld, which can completely remove the strength enhancement that originate from cold work. Now, the type of welds I'm referring to are welds that are carried out after the fabrication of the member. So for example, if you are designing a cold form structural hollow section, which as part of the fabrication process has a seam weld along one of the flat faces, this weld is not considered to affect the strength hardening, the strength enhancement of the member. But if, for example, the structural hollow section is used as a column, which has the ends welded to end plates, when calculating the resistance of the end cross sections, you are not allowed to use the strength, the enhanced yield strength. And instead, you will have to use the nominal yield strength. Now, if you are calculating the resistance of the column against flexural buckling, for example, because the critical cross-section when the column failed due to flexural buckling is at mid-length, if at that location there isn't any weld, then in this case you are allowed to use the enhanced yield strength of the section. Also, if the section has been subject to heat treatments, then you are not allowed to use the enhanced strength due to cold work because the heat treatment might have an annealing effect on the material. Okay, so let's talk about how the stress strain curve of stainless steel affects the buckling behavior. So if you have a look at any of the elastic buckling resistance formulas, you will see that they all have one thing in common, which is that they are all proportional to the elastic modulus of the material. So this is the case for local buckling of plates, for example, column buckling modes, or lateral torsional buckling in the case of beams. The initial modulus of elasticity of stainless steel is similar to the one for carbon steel. But as you can see in this figure, it decreases gradually before the material reaches its yield strength. Because of this reduction in the elastic modulus, because of the reduction of the elastic modulus when the stress increases, the elastic buckling resistance also reduces. And if you want to calculate the elastic buckling load at a given stress level, you will have to first calculate the tangent modulus at that particular stress level, and then you have to use that tangent modulus to calculate the elastic buckling load at that particular stress level. Now, calculating the buckling resistance based on the tangent modulus will require iterations, which is why most of the design codes, that's the reason why in most of the design code, the buckling resistance is calculated using the initial elastic modulus. And then the reduction of the elastic modulus is accounted for by using different buckling coefficients from the one that are used for carbon steel. Now, there are other factors that affect the buckling behavior of stainless steel and also carbon steel members. And these are the geometric imperfections and the residual stresses. Now, the geometric imperfections are generally of the same magnitude for carbon steel and stainless steel. And they can be present at a cross-section level or at a member level. So imperfections at a cross-section level will affect the local buckling resistance of the cross-section. And they will include, for example, the out-of-plane imperfections of the flanges or the web. Imperfections at a member level include the out-of-straightness of a column, for example, which will affect its flexural buckling resistance. As for the residual stresses, they are generally different for carbon steel they're different for stainless steel than for carbon steel because of the difference between their thermal properties. So the main thermal properties that affect the residual stresses are the thermal conductivity and the thermal expansion, which tend both to be larger for stainless steel than for carbon steel. Now, austenitic stainless steels are the ones that have the largest thermal conductivity and thermal expansion. And they are also the ones that show the more pronounced nonlinearity. And because of this, they tend to have the lower buckling performance. Now, not all buckling modes are affected to the same degree by the nonlinearity of the material or the geometric imperfections and residual stresses. For example, global buckling is known to be more affected by this factor than local buckling. Now, for columns with low slenderness, that means relatively short columns, the resistance of the column is governed by yielding. And because of this, the beneficial effect of strength hardening will result in a stainless steel column reaching a larger resistance than a carbon steel column, as I explained earlier. In a long column, or a column with a high slenderness, the resistance is governed by global buckling. And in this case, the compressive stresses in the column will be below the limit of proportionality of stainless steel. And because of this, the behavior will be predominantly elastic. So in this case, the stainless steel column will behave in a very similar way as a carbon steel column. Now, for columns of intermediate slenderness, the resistance is also governed by global buckling, but in this case, the compressive stresses in the column will be between the limit of proportionality and the yield strength. And as you can see in this figure, this is the region where the detrimental effect of the nonlinearity is more pronounced. So because of this, for this range of slenderness, a stainless steel column can be expected to be less strong than a carbon steel column. Okay, so let's talk about how the stress strain curve affects deflection now. So the gradual loss of stiffness in stainless steel implies that the stainless steel member will deflect more than an equivalent carbon steel member. Now, for simplicity, most stainless steel design codes will recommend calculating the deflection using the same traditional elastic equation that are used to calculate the deflection of carbon steel members. But you will have to use the reduced modulus of elasticity, which is calculated using the equation you can see in this slide. This reduced modulus is simply the average between the modulus E sub S1 and E sub S2, which correspond to the second modulus calculated for the stresses in the compression and the tension flange of the cross-section. So this slide shows the equation for calculating this second modulus. So if we have a simply supported beam subject to a uniformly distributed load, for example, the maximum deflection will take place at midspan. And this deflection you will be able to calculate this deflection using the reduced modulus of elasticity and using the traditional equation that is shown at the bottom of this slide. Now, this method of calculating the deflection of stainless steel members gives adequate predictions when the maximum stress in the cross-section is below 65% of the yield stress. For larger stresses, the method becomes very conservative. So for the range of stresses for which this method is applicable, the deflection of a beam that is made out of austenitic stainless steel will be up to 15% larger than if the beam is made out, of carbon steel. And for duplex stainless steel, the deflection can be up to 5% larger. Okay, so let's talk about the fire resistance of stainless steel structures. Here you can see some applications in which stainless steel structures might need to be designed for fire. The fire design of stainless steel structures is very similar to the design of carbon steel structures. So in both cases, the resistance at elevated temperatures is determined in more or less the same way as when designing and when you do the design at normal room temperature. So the only difference is that the yield strength and the elastic modulus that are used in the resistance equations have to be the ones for elevated temperatures. So the value of the yield strength and the elastic modulus at elevated temperature are given as a proportion of the value for room temperature. And this is achieved through retention factors, which are basically the ratio between the property at elevated temperatures and at room temperature. So this figure shows the yield strength of the three main stainless steel alloy families and carbon and for carbon steel, and it shows how these yield strengths vary with the temperature. So you can see that austenitic and duplex stainless steel initially lose strength faster than carbon steel, but at around 300 degrees Celsius, they are able to retain their strength better than initially. And in the case of austenitics, they are able to retain a larger proportion of their strength than carbon steel at temperatures of about 600 degrees Celsius. In the case of ferritics, they behave more or less like carbon steel because of their similar microstructure. In the case of the stiffness or the elastic modulus, there is only one set of retention factors for all the stainless steel alloy families. And this is shown here by this red curve in the figure. So you can see that compared to carbon steel, stainless steels are able to retain a larger proportion of their stiffness almost over the entire temperature range. And this is good when the resistance of the member is governed by global buckling. Okay, so a few words about fatigue before I hand over to Nancy. Austenitics and duplex stainless steel are the alloy families that are most likely to be used for components that might be subject to fatigue loading. Similar to carbon steel, the fatigue behavior of welded joints that are made of stainless steel is dominated by the geometry of the joint. So the crack growth behavior that occur at the welded joint is similar for carbon steel and for stainless steel. So there is a very large amount of tests on austenitic and duplex stainless steel welded joints that show that the fatigue resistance of these alloy families is similar, if not slightly better than the one for carbon steel welded joints. So if you look at the stainless steel design codes that deal with fatigue, you will see that the fatigue resistance of austenitic and duplex stainless steel is calculated using exactly the same fatigue curves that are used for carbon steel. Okay, so now I'm going to hand over to Nancy.
Hello, everyone. Nice to see you've all come back for this second webinar. Now it's time for me to introduce to you some of the design standards for stainless steel around the world. And firstly, of course, the Australian New Zealand stainless steel design standard covers cold-formed structures. So the most recent version was published in 2001, so quite a while ago. And this updated an earlier version that was based on the American Society of Civil Engineers AISC 8 specification for cold-formed stainless steel structures. But in AS NZS 4673, they expanded the scope in 2001 and they covered duplex stainless steels. They covered some useful explicit design rules for flexural buckling and also some rules for cold-formed hollow section members and their welded connections. Time has passed and now this standard has been withdrawn by the standards bodies. So 2 comments about that. First of all, please remember that this is a standard for designing cold-formed members. So structures like this bridge I showed you last week, you couldn't use this standard for designing that, so not suitable for the heavier plate hot-rolled sections. And my second comment is that despite its being withdrawn, it seems that the standards body can say that it can continue to be used if there's no replacement document readily available. So I guess that is the case. You have the opportunity to continue using this if you're designing cold-formed stainless steel structures. I'm going to tell you about some other alternative stainless steel design standards now. And the first is the Eurocode, of course, very very close to my heart, as I've chaired the technical committee for this standard for I don't know, 13 years. So here we are. Part 1.4 is in the Eurocode 3 ecosystem, and there are many parts of Eurocode 3, design of steel structures. In fact, there are more than 12 because we've got new ones now for beams with holes in the webs and for design by finite element analysis. But let's just zoom in on 1.4. So it's called Supplementary Rules for Stainless Steel. So there's a clue, a big difference to the Australian standard and the American standard I'm going to tell you about. It's not standalone. This standard is quite short, I think 35 pages, something like that. And it just gives supplementary rules where you can't use the carbon steel rules that are given in other parts of the Eurocode. It has a broad scope, so it covers hot rolled, welded, cold formed, as well as bar products. And it covers 3 families of stainless steels: ferritic, austenitic and duplex. That's the same as the Australian, New Zealand standard. So within the standards, provisions where required are given for members and connections where stainless steel needs specific rules. But it points out to other parts of Eurocode 3 for design at elevated temperatures, for fatigue and design of shells. One important thing to notice is that there are different partial factors for stainless steel. Here I've put the gamma M0, gamma M1. They are 1.1 compared to the carbon steel values, which are 1.0. What's been the timeline? Well, it was published in 2006. That was based on a collaborative European project mainly. And then in 2015, there was a substantial amendment. So much research had been done around the world in the intervening years that we were able to put in more competitive rules, for example, for section classification. And we put in a complete annex giving a procedure for selecting the right alloy for different atmospheric environments. Then just recently in 2020, the flexural buckling curves were also amended. So if you happen to need to use the Eurocode for stainless steel, just make sure that you are using the 2020 version, because that will have the full table of flexural buckling curves. Some of the curves got stricter and some new curves were added in the 2020 amendment. On the basis of just better understanding. I mean, there has been an explosion of research activities in the last 20 to 30 years on structural stainless steel, as it's been understood to be such a useful material for certain types of structures. Looking ahead, we have generation 2 of the Eurocodes, which has been a gargantuan task. I think they thought it would take 6 years, and you can see it's going to be a lot longer than that. All the parts of the Eurocodes have undergone revision, so that's timber, concrete, aluminium, everything, with a view to improving ease of use, getting more comprehensive rules, more accurate rules, etc., etc. This was really important for stainless steel because it wasn't a very mature standard when it was published, because it was the first standard for many European countries covering stainless steel. So we've taken the opportunity to include a wider set of design rules covering more member types and more design scenarios. That actually is now complete, but it's undergoing a long and drawn out process of being affirmed, being translated, and the first generation Eurocodes will not actually be withdrawn until 2028, which is ever such a long time in advance, but they are beginning to come on stream, but you can't use them without the national annex, which each country has to write for each part of the Eurocode. So you see, we're going to be quite busy over the next few years writing national annexes. Can I remind you of the design manual for structural stainless steel, freely downloadable at this link, that not only interprets and explains the Eurocode design rules, it gives those most important design examples, which are so helpful. And there's also a commentary, and there's some simple phone apps for calculating section properties, etc. Now we move to the States, and firstly we consider the American Institute of Steel Construction Design Rules. So let's start in 2013, where there were no design rules for hot rolled welded stainless steel products. And SCI was invited to write an AISC design guide, which covered the design of these products. We wrote it as a sort of a mock specification, not covering all the possibilities, but just, you know, it was a mark in the sand, a start. And then people seemed very interested in it. There were lots of requests for information. So AISC decided they needed to have a complete legal stainless steel design specification. So that was published 2021, and it is called AISC 370. So it's a sister specification to the carbon steel specification, which is AISC 360, which I expect you've heard about. What's the scope of 370? Well, it focuses on sections, bar, and plate, and it mainly covers the austenitic and stainless steel families of stainless steel. Not ferritics, because you may remember last week I told you ferritics really are more for the lighter gauge, thin material. And in the States, there is also interest in the family of stainless steels called precipitation hardening alloys. So we cover them also for tension members and fasteners. This standard, freely downloadable from the AISC website, and it comes with a commentary and covers fire and fatigue. So it's quite comprehensive in its scope. It has an accompanying specification in the style of AISC design specs, which is called the Code of Standard Practice for Structural Stainless Steel Buildings, which basically covers trade practices, the contractual arrangements between parties. And the third document in the trilogy from AISC is the second edition of the Design Guide 27. So this becomes really like a steel construction manual accompanying the specification. And it has more information on alloy selection. It does a comparison of stainless carbon steel. It has design tables, lots of them. It's like 400 pages long or something. And it has design examples also. You have to pay for this, $60 from the AISC website. Now, let's do a full circle and go back to ASCE 8, which was the first, I think, design specification for stainless steel, published in, I think it was 1968, then revised in 74, revised again in 1990, thereabouts, then revised in 2000, and then it got stuck. But just recently, Professor Ben Schaefer led a group to undertake a significant revision, and this was published at the end of 2022. well, actually, it was published in 2023, but it's got the date 2022. So what's it cover? It covers cold-formed stainless steel made of austenitic, duplex, and ferritics, focusing on slender cross-sections, open shapes, made from coil and sheet. And it's very closely based on the American cold-formed carbon steel specification, which won't surprise you, AISC S100. You'd want to use it if you're manufacturing or designing studs or tracks, purlins, girts, panels and decking, cladding, roofing, linings, those sorts of components. A comparison with ASCE 8 and AISC 370 is shown on this slide. So as I said, ASCE 8 covers the ferritics as well as the austenitic and duplexes. Ferritics, because of course these are light gauge application, focusing on coil and sheet from the AISI tradition following ASCE processes, whereas AISC 370 is the heavier sections. So these standards, yes, of course, they're similar because they're covering stainless steel, but there are quite a few differences. 370 gives simpler solutions. It's really specifying with the engineer in mind, perhaps even the engineer in a hurry in mind. ASCE 8 gives more exact solution, it's more complex, and it's focusing perhaps more on the manufacturer, where it's absolutely critically important to get the final 5% of capacity out. There is some overlap in scopes, and this is permitted in the States. I could go on for quite a few more slides, but we've got some other important stuff to cover. But there is a Chinese specification for stainless steel covering cold formed, hot rolled. And although it was published in 2015, they're revising it. There are Japanese specs too, Korean spec. Haven't got pictures of those, but you get the message. Now, I'm going to apply what Francisco was saying and give you a few examples of how the differences in stainless steel behavior are actually put into design rules. So the first thing to say is don't panic. Same approach as carbon steel, of course. Be careful you use the right resistance factors for stainless steel. I pointed out that for the Eurocode, they're different. For AISC, they're the same. There's no difference in rules for tension members or restrained beams, but there are different rules for stainless steel for some of these other topics. And I'm just going to, I think I've got 4 slides giving an example of how these other topics are dealt with. Firstly, alloy selection. So the American standard, Eurocode, AISC, don't know about the Chinese standard, can't read Chinese. They all give very helpful guidance on alloy selection, which is really important. And I've just put on this slide an example of swimming pool guidance. I think someone maybe asked it last week. It was in my mind, but it's important to know this, that these are inside swimming pools, highly corrosive environments, particularly at ceiling level, where the contaminants condense on members and build up very high concentrations. It's not a problem if the component is immersed in pool water because it washes off the contaminants. So there are very clear rules for load-bearing members which can't be easily cleaned, like in suspended ceilings. You should not use 304 or 316, but a more highly alloyed, considerably more highly alloyed stainless steel, such as the super duplex or 6% molybdenum austenitic stainless steels. If you are put in charge of inspecting a pool that does have 304 or 316 in load-bearing members that can't be cleaned regularly, then they really need to be replaced or inspected very frequently. That's an example of alloy selection guidance. Completely different example here concerning cross-section classification. Now it's necessary to check the width to thickness ratios of elements of cross sections if they're subject to compressive stresses, and you compare them against limiting ratios because you're concerned about the possibility of the cross section to buckle locally. Here's an example there from AISC 370 where the stainless steel limiting values are compared against the carbon steel values. Why are they lower? Well, it's because stainless steel has a non-linear stress-strain curve, and it does have an adverse effect on local buckling compared to carbon steel. So don't be surprised if you see lower values. Column buckling curves. Now here, again, I've taken an example from AISC. And you will see that for stainless steel, there are actually 3 different global buckling curves for columns. And they actually depend on the cross-sectional shape of the column and the axis of buckling. Whereas for carbon steel, which I show in the black line, there's just one curve. Why did we complicate things by putting in 3 curves? Well, stainless steel costs more, so it's worth the extra effort, hardly any effort at all, really, of using the more accurate curves. Another difference you'll see is that the stainless steel curves have a plateau, a yield plateau, which means that if you've got a short column, there's no reduction in strength as a result of global buckling. So quite significant differences here between the column buckling curves for carbon steel and stainless steel. Here's another example in all the stainless codes, and that is the material model. Now, back in the 1940s, we had 2 people, Mr. Ramberg and Mr. Osgood, and they came up with this very nice equation for modeling materials. I think they were working on aluminium for the aeronautical industry, modeling nonlinear stress-strain characteristics. And so this has been adopted by materials like stainless steel and aluminium. For carbon steel, which is shown on this graph, you generally use a bilinear curve or perhaps bilinear with hardening or quadlinear. The amount of nonlinearity is determined by this exponent n, which is called the strain hardening exponent. So the higher it is, the less nonlinear the material. So carbon steel would have an exponent of infinity. Structural analysis. I don't think we've talked much about this, but again, the rounded stress-strain behavior of stainless steel means that frames made of stainless steel are affected by larger second-order effects. So if you compare the design rules for carbon steel and stainless steel frames, you'll see that there are some differences in the way these effects are calculated. And there's also a lack of yield plateau for stainless steel. So that means that plastic hinge analysis, in which you've got the plasticity concentrated at a discrete cross-section, it's not so appropriate to represent the behavior of stainless steel frames. And instead, we've introduced the concept of a plastic zone analysis, which is able to spread, where it considers the spread of plasticity through the cross-section and along the members. So that's what you'll find if you look in 370 or the second generation Eurocode. Francisco mentioned the advantage of the strength enhancement due to cold forming. So I just put here a table showing you the types of enhancement you might expect to get. These are in inches, if you're wondering why they're such very small hollow sections. Again, I've used the AISC design rules to calculate these numbers. So what can you see from this table? First of all, much more advantage for austenitics because they have more non-linear characteristics than the duplexes. And you get a greater strength enhancement as the section becomes stockier. So here we have the 4" by 4" by 0.25 compared to a 4" by 4" by 0.12 and a significantly larger strength enhancement. I'm going to stop on that topic, but just to let you know that at the moment, there are no rules in American or European design standards covering stainless steel, composite design, or seismic design, but there's a lot of work going on. Composite design in Australia and in the UK, us included, and probably elsewhere too, Singapore, I think, and seismic design. So we're going to talk through the work that we've done and others have done on these two topics in 2 weeks' time. And we're also going to talk more about the continuous strength method and new design rules for slip critical bolts, which of course are very important for structures like bridges. I have a couple of minutes to talk a little bit about stainless steel connections. Firstly, bolted connections. I think I mentioned it last week, but it is very important that the corrosion resistance of a stainless steel fastener should be at least as good as the material it's joined. And not only the fastener, of course, the washer and the nut. So you should use A4 bolts or better to join 316 material, and it's important not to use galvanized steel fasteners because their corrosion resistance is not equivalent to A4. Generally, design rules are the same for carbon steel, stainless steel bolted connections. There's one exception I'm going to tell you about on the next slide. It is important to take measures to avoid galling, which happens with materials like stainless steel that have the passive film. And this is where when the surfaces are under load and in relative motion, they can seize and make it very difficult to fasten the connection. It's well documented measures to avoid galling, lubrication, reducing the bolt tightening speed, lots of guidance on that. Even making sure that the threads and the bearing surfaces are undamaged and very clean. I mentioned there was one difference in the design rules, and that is for the bearing resistance of the bolted connections. Again, because of this load deformation characteristics, for carbon steel, the load deformation curve flattens off, but for stainless steel, it continues to rise. And so you need greater clarity in defining the bearing capacity. Otherwise, it would just go on and on and on. So we've introduced that and got different failure definitions depending on the thickness and whether it's strength or deformation that are the governing criteria. So very simple rules to apply. Finally, on bolted connections, what to do if you're connecting with a carbon steel member. And again, there is guidance in all the design guides and specifications about this. It's not a problem if there's no water. But if there is water, and particularly if it's salt water, then consideration needs to be given to either exclude water from the joint or to isolate the metals. Isolation tends to be materials like thermoset plastics, like neoprene, nylon, PTFE. This isn't new guidance. This has been used in the pipework industry for decades and decades, so these products exist. It's very complicated to predict whether bimetallic corrosion will occur, and also to what extent it will occur. The less noble metal, the anode, so say if you're joining carbon steel to stainless steel, it'll be the carbon steel that would corrode faster than if the metals were not in contact. So here I've said carbon steel, zinc, aluminium, they would corrode in preference to stainless steel, which would form the cathode in this galvanic cell. But you know, that's not a done deal. It depends on how corrosive the electrolyte is, and it depends on the area effect. If you have a carbon steel fastener in a stainless steel plate, that's bad news, and you really don't want to do that, because the carbon steel bolt will corrode quickly, providing there's a conducting electrolyte present. Finishing off now, welded connections. Stainless steels are weldable. Duplex stainless steels do need more control because of their duplex microstructure. You do have to control minimum and maximum heat input during welding. There is lots of guidance on how to do that. For example, information produced by IMOA has some very good leaflets. Weld distortion needs to be taken into account because of the thermal properties, as Francisco was talking about earlier. But like for carbon steel, use suitable welding procedures, qualified welders, compatible consumables, and indeed you have a code on structural steel welding for stainless steel. AISNZS 1554 Part 6. Finally, can you weld stainless steel to carbon steel? Yes, you can. Use the right consumable though. It has to be over-alloyed. And if it's in a corrosive environment, the coating that's on the carbon steel must extend over the weld onto the stainless steel by a margin of 50 to 75 mil. Someone asked last week about stainless steel section availability. So Paul Gapper spent his weekend doing a bit of research, and here's the answer for you. I hope you're on this webinar this week. So these are typically some of the stainless steel structural products that you can get, mostly local, some are short lead times from Asia. So these would be austenitic angles, channels, I-beams, flat bar. Duplex would be special orders. Thank you for listening. To summarize, designing stainless steel really is quite straightforward, following the same general approach for carbon steel, and there are modern, comprehensive design standards available, plus supporting design resources. Next week, we're doing something completely different. I've invited my former colleague, Catherine Cushell, to come and talk about stainless steel reinforcing bar. And then in 2 weeks' time, it'll be Francisco and I again, and we're going to talk about some of the research initiatives, seismic design, composite design, and other issues. If there are other topics you would like us to cover, then in the feedback form, let us know in case we can squeeze them in.
Thank you very much, Nancy and Francisco. Dear listeners, if you have any question concerning this presentation or about any nickel-related topic, Kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner, Technical Help. Click on it, register, it's free of charge, and fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.